All right, class, now I'm going to cover what is section 5.3 of the homework. This is actually section 5.2 of your text. Again, they updated the sections in the textbook, but not in the homework. I apologize for that. But section 5.3 of the homework talks about complex zeros and the fundamental theorem of algebra. So a variable in the complex number system is referred to as a complex variable, okay? And a complex polynomial function of degree n is a function of the form f of x equals a sub n, x to the n, plus a sub n sub 1, x to the n plus minus 1, all the way to a naught, right? Where an sub 1, a1 and a0, a naught are complex numbers, and n is a non-negative integer, and x is a complex variable. So, as before, a sub n is our leading coefficient, and if a complex number r is a zero of our polynomial, then f of r equals 0. So the remainder theorem works, which is really cool. It's also important to note that this looks exactly like what a normal polynomial does, right? It says that my constants are complex numbers, okay? But that's not always going to be the case because they could also be real numbers. Real numbers can also be considered complex. The fundamental theorem of algebra is this. If every complex polynomial function f of x that every complex polynomial function of degree n is greater than or equal to 1 has at least one complex zero. And you're going to see why that's kind of a silly theorem in just a second. So if I have a complex polynomial function, I can pull it apart into its linear factors and it'll still have like a leading coefficient. So a sub n, r sub 1, and r sub 2 are complex numbers. So that is that every complex polynomial function of degree greater than 1 has exactly n complex zeros, some of which may repeat, and that's okay, right? We can have zeros with multiple multiplicity. A polynomial f of odd degree with real coefficients has at least one real zero. That's the corollary we get from this. So I could have a polynomial that looks very much like the polynomials we were working with in the last section that all had real zeros and rational zeros, and we're going to start to find some complex zeros. So keep that in mind. So the first thing we need to know is the conjugate pairs theorem. So if I have f of x as a polynomial whose coefficients are real numbers, and if I have r equals a plus b is a zero of that polynomial, then the complex conjugate r equals, that's typically denoted a bar, r equals a minus b is also a zero of f. And why is that? Well, I first just want to say that the product of complex conjugates becomes a real number. So let me show you an example. So here I have complex conjugates. So if I have 3 plus 2i, its complex conjugate is 3 minus 2i. If I have 4i, its complex conjugate is negative 4i. When you multiply by the complex conjugate, the complex cancels out. I could also have negative 5i and negative 5i squared. And negative 5 minus I. Why don't I go ahead and multiply these two together and show you how the complex part goes away when you multiply a complex number by its conjugate. Friendly reminder, I squared. Nope, friendly reminder that I equals the square root of negative 1. So if I have I squared, that's the square root of negative 1 squared. Square roots cancel out squares, so I squared really equals negative 1. So let's go and take negative 5 plus I times negative 5 minus I and see what happens. So if I have negative 5 plus I times negative 5 minus I have to FOIL this out. That's how we multiply complex numbers, by FOILing. Negative 5 times negative 5 is positive 25. Negative 5 times negative I becomes a positive 5i. I times negative 5 is negative 5i, and I times negative I is negative I squared. You can see my middle terms cancel. So I have 25 minus I squared. Well, I squared is negative 1, so I have 25 minus negative 1. That gives me a 26. When you multiply a complex number by its complex conjugate, the complex part cancels out. The complex part goes away. So we're going to use this theorem to find the zeros of complex polynomials. So if I have a polynomial whose coefficients are real numbers and I find a plus bi is a zero of f, then the complex conjugate is also a zero of f. So why don't we go ahead and find zeros using the conjugate pairs theorem. A polynomial of degree 5 whose coefficients are real numbers has the zeros negative 2, negative 3i, and 2 plus 4i. I need to find the remaining two zeros. I know this has 5 zeros, or it could have at most 5 zeros because it's a degree 5 polynomial. So my zeros are negative 2, negative 3i, but I also have to have the conjugate of negative 3i, which is going to be a positive 3i. Then I have the zero 2i, 2 plus 4i, sorry. So I have to have its complex conjugate, which is 2 minus 4i. Next, I have a degree 3 polynomial. It's going to have at most 3 zeros. I have that one of my zeros is 4, and one of my zeros is 3 plus I. So my zeros are 4, 3 plus I, and I also have to have the complex conjugate of 3 plus I. So I then have 3 minus